evening and welcome to Tinkering with Atkelar. This episode is a special treat. As you might have guessed, I frequently watch other tech channels on YouTube. One of them is Curious Mark, who always is good for interesting restorations, and I'm not only talking Apollo here. In one of his more recent videos, he was showing two HP 410C VTV amps, that is, vacuum tube voltmeters. He set out to restore both, but one of them had a completely broken mains transformer, so I contacted Mark and asked if I could have a go at it, since I did rewind several transformers before, and he agreed. So here we are! On a side note, I just upgraded my bench cameras, so I'm starting to upload stuff in 1080 now. But I have quite a bit of footage from the old cameras left, so expect a bit of mixed quality for a few episodes. And now, back to our program. From the original video, I already knew that the mains transformer is broken and that the power switch is not working properly. The amplifier board is also questionable and the wires and AC probe are missing. So, as it stands, it's a pretty brick. Let's start by taking things apart. The power switch was also marked as not properly working. Mark said plenty of contact cleaner made it work again. Checking the neon indicator inside the switch next. It is wired into the 150 volt path of the primary, so it should light up at about 100 volt, give or take. But no, after cranking up the voltage a bit, it does come on at about 130 volt, which is way too high. The bulb must be on its way out. Since Mark spent a good time cleaning the unit, it was a bit easier than other devices I had, but there was still quite a bit of gunk in all the crevices that were not accessible in an assembled state. I hate to do it because the switch has no screws, but if I want the original look and feel, I have to open it up and replace the neon at least. Also, while I'm in there, clean the contacts and remove any soot. The switch is held shut with the pinned over rear end, so I have to carefully pry that apart again. Since it's very soft aluminium, it does crack in several places, but overall, success. The inside of the switch comes out nicely. The switch has an interesting construction. I thought it would be a bit like a ballpoint pen by rotating or latching some contacts, but no, it just converts the push button motion into a rocker switch motion in the back. The neon is held in place with a pair of concentric springs. I could not locate any neon bulb in that size. I found similar bases, but the tip of those lamps was too long and those would not have fit into the button. So, remove the bulb and reuse the base. I thought that the tip of the base was like a small nail that can be pried out. Whoops! No, it's actually an eyelet with a wire soldered in. Now I have to repair the insulator. I put in the new bulb and solder it in place. For the insulator around the eyelet, I just apply a bit of epoxy. Putting the switch back together was quite annoying. There is exactly 0 tolerance inside that package. If the spring for the neon are out by even half their diameter, it won't fit together. I lost count on how often I had to slide that cover off and on again until it finally snapped into place. Last but not least, after a quick function check, peening over the case again so it stays in place. Doesn't look too bad in the end, only a few tiny fragments chipped out. Here's where I finally spotted the broken 7 ohm resistor that Mark mentioned. I thought it was one on the power supply board, but it was one for the input divider network, so it does need to be quite accurate. Last on my list, the electrolytics. I differ in opinion with Mark on that question. I don't like to keep wet components after a certain age, but just to calm everybody out there, I checked the DC filter cans. The high voltage 4x20 microfarad one seems okay, but the 2x1200 microfarad one was not even registering as a capacitor anymore. I gutted them as usual. This time I even managed to save the plastic cover. The new capacitors are the same rating, but tiny. Easy work. After my last restoration, I pondered my options for closing these cans and came to the conclusion that a dab of epoxy should be fine. I just have to be careful when mounting them. The case probably can't take much side force because the epoxy snaps off the aluminium. But this way they look factory again. After taking things apart, I checked the wiring of the transformer. Yes, indeed, both of the primary windings are shot. And it's even worse. The high voltage secondary also has no connection between any of its taps. At this point, I guess it wasn't just a regular overvoltage situation as Mark suggested. He mentioned that somebody might have plugged it into a 230 volt outlet while set 250 volt. But that amount of damage seems too much for just double the expected voltage. Besides, the fuse would have blown first. I'm more leaning towards a direct lightning strike into the mains line. Either that, or it suffered extensive user abuse. I have to say, this one is certainly the hardest one to take apart that I had on my bench so far. There is no way that I could get any of the laminates to move with all the lacquer in between. Thankfully, they used a cardboard-like wedge on one side that is just thick enough to be cut away with a fret saw, and eventually I could start separating the sheets with a knife. Looking at the bobbin, I think I have to do some careful planning. there is next to no air between the windings and the iron core. And since I don't have an industrial winding machine for constant layers and perfect fitting wires, I need to make some trade-offs to fit enough copper on there. Here's where a closer look at the circuit is called for. How are the secondaries organized? What is the option for the primary? First off, I don't want to lose any features on the outside of the case, so the 115 and 230 volt switch needs to stay. Thus, the primary has to remain split. But the secondaries show potential, and not just electrical one. We can see here that there is a 6 volt winding, which turns out to be the standby heater for the AC probe. Whenever the meter is not in AC voltage mode, this one supplies 6 volt to the external probe tube to keep it hot. In AC mode, the heater is switched to the 6 volt DC supply that heats the internal tube. If I ditch the standby heating, I could save an entire winding. But it gets even better. The DC supply uses full wave rectification via silicone diodes, but for some reason they use center tapped windings. This is clearly not useful for any purpose in this circuit. Why was it done like this? My bet is that HP had this transformer around from other tube circuits, where this approach is better because you only need one rectifier tube instead of two. But here, this offers no advantage over a regular full bridge rectifier. So, add 4 more diodes and ditch half the secondary windings. Important space saver. During unwinding, I tried to find the break in the wire, but since the lacquer extended all through the windings too, the wire broke several times anyhow, and I had to cut off chunks with brute force. I have no idea where the bad part was, but there was a considerable black spot on the primary side. Winding the new primaries first. Followed by a sandwich of insulation and 2 shielding layers. A comment on an older video suggested that these might cause the transformer to heat up because they end up as one winding and would make heat. I think they originally were a single loop, but I can see the argument, so I'm wrapping them with a bit of insulation between the ends so they don't make contact. The high voltage secondary uses very thin wire, very annoying to work with. And finally, the thicker 12 volt layer that provides power to the 6 volt regulator. A good layer of insulation, the solder points and the label make the final additions. Stacking the laminates. Because of the lacquer residue and the slight bend that they all have now, it is impossible to get all of them back in. Based on my calibrated eye and some experience though, I'd say that the original was way overpowered anyway. A VTVM needs a heater supply and a few milliamps for the transistors in the amplifier circuit. So if the total power consumption is more than a few watts, I'd be surprised. And this one looks more like 30 to 40 watts to me. I think it'll work perfectly fine with a bit less iron. Validation time. Powering up the transformer and checking the output voltages. Looking good. The case parts also get a good scrub now that they are fully exposed. I also give the AC probe socket a good clean. I follow my general rule: leave no screw unturned. Cleaning the wafer switch is next. I really don't want to remove the wiring in this case. The tangle of wires and resistors is a bit much, but there's a layer of filth inside that mess, and the contacts might also benefit from a bit of Q-tip aided cleaning. I remove the mechanical part of the switches, add fresh lubrication and clean everything between the wafers now that it's more accessible. Putting them back together was fiddly. The stack has spacers, and the spacers have spacers. Why is it so weird? The wafers are some sort of ceramic, so they are very brittle. Tightening the screws with the metal spacers would probably break them. So HP put little plastic washers between the wafer and the spacers to take most of the mechanical load. Smart, but trying to maneuver those things into place in situ caused lots of moments. The AC0 potentiometer also gets a good inside-out cleaning and fresh lube. Now a side project. The device came with the usual old power socket. I can't find decent cables for these anywhere, so like with the other similar devices, I'd like to replace it with a new IEC connector. Problem: it won't fit. It would either be blocked by the case or run into the fuse holder. Time for a harsh decision. I got these combined IEC and fuse holder sockets. That one covers up the old socket and the fuse holder. So let's mill out a bit and mount it. Assembly time! Starting with the selection switches to prevent any wires from snapping off. The 7 ohm resistor was unobtainium. The only one I found had 10 watts, which would have looked quite funny, but not practical. So I got two 14 ohm resistors instead and paralleled them up to get one 7 ohm within the 1% tolerance specified. For the grounding wire, I found a nice silicone wire in the appropriate diameter, adding the strain relief and soldering it to the standoff. The case comes together nicely until it is time to add the backplane. The wiring there requires some dexterity. Sheesh! The power supply board gets a well-deserved scrub to remove the old flux residue. HP used what appears to be regular spade connectors to clamp into the PCB. Interesting design. I bet they sell it as some impedance-optimized contact system, when in reality they just save a few bucks on connectors. But when I got it, 2 wires were already soldered to the PCB instead, and several other connectors were broken. They hadn't made them for that kind of load. I got similar ones here, and with a bit of tweaking, they fit in nicely. Finally, After connecting all the loose wires and adding the diodes for the DC rails, power on time! I bring up my Variac slowly to make sure that nothing is shorted and the polarity for the capacitors is correct. After checking the power supply board with my thermal camera, it seems that the 9V Zener diode is getting a bit toasty. I thought it might be broken and replaced it with a combination of new ones, but they also heated up considerably. It is here where I wanted to try out different positions on the mode switch to see if that changes anything on the voltages. And youch! That was unexpected! A quick check with the meter confirmed. Between the circuit ground and the chassis ground there's 115V AC. That tickles! But where's that coming from? And yes, that might be the reason why that diode was heating up. After lots of poking, prodding and testing, I came to the sad conclusion that the high voltage secondary winding was shorted to the shielding layer inside the transformer at about 2/3 of the windings. No idea why, but I had to rip out the transformer again, unwind and rewind it. I added an additional layer of insulation between the shield and the secondary, so it should be fine now, hopefully. I didn't film much here, since it is the same process all over again. After connecting everything back together, success! I got the expected voltages and the case is now tingle-free. This is now a good time to conclude part 1 of the project. What's left to do? Clean and check up on the PCBs, the meter movement, add the missing wires and probes, and rebuild the new AC probe. Parts are on order. This time I have no idea if part 2 will be the next video or not, so stay tuned. Thank you for watching and Mark for sending over the project. See you next time!